So in this video, we're going to be continuing on with the topic of the shape of a graph, but we're going to be putting everything together. We're going to be using the first derivative test and the second derivative test to actually graph this function right here, x cubed minus 12x. We use this function in both previous videos on the first derivative test and the second derivative test. So we're just going to do that, use that same information, but in this video we're going to be graphing the function. We're going to be graphing this function. So we're just going to be making a general graph of this function, but we're still graphing it. So first things first, let's actually derive the first derivative and the second derivative of f of x. So the first derivative is just 3x squared minus 12. The second derivative is just 6x. So based off of the previous two videos, you guys should go watch those two videos first and then come back to this, because this is putting all of that information together in order to graph it. So in the last two videos, we determined that for the first derivative test, we want to set the function of the first derivative equal to 0, so we can get the critical points, and we determined those critical points to be -2 and 2. And for the second derivative test, we said that we want to determine the inflection points, that those points are where the concavity changes, and those points are where f double prime of x is equal to 0. And we determined those the inflection point. They could be multiple, but in this case it was just one. The inflection point was 0. So let me actually write x is equal to, so the critical points are x is equal to -2 and 2. Inflection points are x is equal to 0. So now, in order to first, the next thing we did was basically draw a coordinate, like a plane, in order to just look at where the first derivative and the second derivative are positive and negative. So let's actually do that right now. So there's gonna be different functions. So f double prime in the bottom. All right, f prime, and then f. So this is the original function, the derivative of that function, and the double derivative of that function. So first things first, we started off with the first derivative test, so let's continue with that. So we know the critical points are -2 and 2, so let's list those here. -2, 2, right? Now, in the first video, we said that to the left of -2, the first derivative, aka this right here, 3x squared minus 12, is actually positive. To the left of the critical point -2. And then we said that to the right of that critical point, of that same critical point, to the right of -2, the first derivative is actually negative. And to the left, to the right of the critical point 2, we said that the first derivative is positive. And to the left of this critical point, it's still negative, because this -2 to 2 is the one whole domain. So now that we've gotten the value, the signs for the first derivative, we know that from -infinity to -2, so -infinity to -2, the function is actually increasing. And we know that from -2 to 2, the function is decreasing. And we know that from 2 to infinity, the function is actually increasing. So now at least we got down where the function is increasing and decreasing. Now we can move on to the second derivative test. And the second derivative test will show us the concavity, right? What does the curves of the graph look like? So first things first, we should put down the inflection point. Inflection point is 0, right? Inflection point is 0. So I'm gonna put it like this. This is where f double prime is equal to 0, right? This is the inflection point. This is where concavity will change. So we determined in the previous video of the second derivative test, we determined that on the left of this inflection point 0, the second derivative is negative, and on the right of the inflection point, the second derivative is positive. So this indicates a change in concavity. So since the concavity changes from concave down to concave up, we know that it's going to there's going to be a relative maximum at a certain point, and there's going to be a relative minimum at a certain point. So first things first, now that we have all the signs of the first derivative test and the second derivative test, now we can start comparing. So the first sign we see is over here. So it says that the first derivative is positive in between negative infinity and negative 2. And the second derivative is negative in between negative infinity and negative 2 as well. So we want to basically have a function that is concave down, and this the second derivative is negative, so we know it's going to be concave down. So we want the original function f to be concave down, but it should be increasing. The function should be increasing. So if we look back at the definition of concavity, we remember that tiny table. If you want something concave down and increasing, it looks something like this. So in between negative infinity and negative 2, the function, it looks something like this. And let's just make a dotted line here. So in between negative infinity and negative 2, the function looks something like this. Now, moving on to the next subregion, in between negative 2 and 0, we're gonna include 0 because that's where the concavity will change. So the first derivative is telling us that the function is gonna be decreasing because it's negative. It's decreasing, it's negative, and it's gonna be concave down because the second derivative is negative. So when we want something to be concave down and to be decreasing, it looks something like this, like that. So in between negative 2 and 0, the function looks something like this. Now we can move on to the subregion 0 to 2. Now we know that the concavity since 0 is the inflection point, concavity is going to change. So we know that it's going to be changing from concave down, right? This was all of this was concave down. Now we know it's going to be changing from concave down. Now it's going to be concave up. So let's look at the first derivative of the function. So it says that the function is the first derivative of the function is negative in between 0 and 2. In between 0 and 2, therefore the function is decreasing. The function is decreasing. And when we look at the second derivative test, we say that the second derivative is actually positive in between 0 and 2. That means that the function is going to be concave up in between 0 and 2. So it's going to be concave up, but it's going to be decreasing. It's going to be a decreasing function, but concave up. And in order to when we want a function to be concave up and decreasing, it looks something like this. So this is concave up. So this is concave up, and it's still decreasing. So the function f of x looks something like this, in between 0 and 2. Now, the last subregion, from 2 to infinity. So we see that the first derivative is positive from 2 to infinity. That means that it's an increasing function. Increasing. And the second derivative is actually positive as well, so it's concave up. So it's going to be a increasing function, and it's going to be concave up. And when we want a function, when we want something to be concave up and increasing, it looks something like this. So the function f of x looks something like this, in between 2 and infinity. So now that we figured out how the concavity changes and the signs of the first and second derivatives, now we can start graphing. We can actually start graphing this function. We could just make a general graph. We don't need to make a very specific graph just yet. We need a little bit more information to do that. But for now, we are able to make a general graph of x cubed minus 12x. So let's actually do that. So let's graph. So let's just write down the points. So first things first, when we graph, after we do all of this work, when we get to the graph, first thing we're going to do is make this plane, and we're going to mark down where the critical points are and where the inflection point is. So I'm going to make the critical points red and the inflection point blue. So we know there was a critical point at 2, and there was a critical point at -2. And then we know there was a an inflection point at 0. So 0 is where the concavity will be changing for this graph. So now we can compare what we have over here and basically build this graph. So from -infinity to -2. So we graph this the function based off of each subregion. So right now we have one subregion here, another one here, another one here, another one here. So 4 total subregions, and we have to graph based off of each of these regions. So we're gonna look from left to right. So this first subregion, -infinity to -2. So right here, -infinity. So we know -infinity is here. So it's from here to here. And this right here is just positive infinity. So we're looking at this region right here. So what we determined is that this f of x is increasing, but it's concave down from -infinity to -2. So so we know it's gonna look something like this. It's gonna be something like this. So from 2, it's gonna look something like this. And then we can actually, if you wanted to, you can evaluate -2 at in the original function. So let's actually do that. to get a y value. So let's do f of -2. So it's going to be -2 cubed minus 12 -2. And we get -8 plus 24. And this is 16. So this value right here, we could say is 16. So this right here. So we got through one of the subregions. The next subregion is in between -2 and 0. And this is where the concavity will be changing as well. So right here. The next subregion is right here, -2 to 0. So we're going to start from where we ended, right? We determined that in between -2 and 0, the function is actually concave down and decreasing. So the function is going to look something like this. Like that. And let's just do it like that. So you see how in between -2 and 0, function is decreasing. However, but you see that in between -infinity and -2, function is actually increasing. But it's still concave down. Now the next step is looking at the next subregion. Now we know that 0 is going to be the inflection point where the concavity changes. So it's going to be changing from this concave down figure to something that looks like a concave up figure. So let's see what happens when we add in the next subregion. So the next subregion is 0 to 2. And we determine that the function is actually concave up. And it's decreasing in between this subregion. So 0 to 2 is right here. Right? And we can actually make this concave up. So let's make this concave up from here to here. Now you see the concavity did change. So let me actually make this a little neater. So the concavity changes here, right here. So you see, at x is equal to 0, the inflection point, the concavity changes. It changes from concave down, now it's concave up. Now, moving on to the next subregion, which is in between 2 to infinity. In between 2 to infinity. So, in between 2 and infinity, we determine that the function is going to be concave up, but it's going to be increasing. So it's going to look something like this. And there you go. This is the function of x cubed minus 12x. This is just a general function of the graph.